The mic on? Yes. Welcome to QIRG, Quantum Internet Research Group. Still proposed as of our current status. Let's see, I am Rod Van Meter and I will be running today's meeting. Welcome, and the blue sheets have just begun circulating around, so please sign in as the blue sheets come around. Let's see, so we have both a scribe and a note taker set up. Thank you. Let's see, so today you all know where and when we are. For those of you who are new to what we're doing, just a quick review of the current status. The idea of this was originated by Stephanie Vayner in January of 2018. I presented remotely at the IETF Open in March 2018. The mailing list opened that month. It's ongoing. The traffic level is sort of low to moderate. We were approved as a proposed RG on November 6th last year in Bangkok, or just prior to Bangkok. And the tentative proposal is or was to meet one time a year at IETF, once a year at a quantum conference, and once per year in a virtual or online meeting. So far, we have actually achieved 3 face-to-face meetings at IETFs 103, 104, and 106. And so far, 4 online meetings, all in the last couple of months. I'm focusing on one of the drafts in particular that Wojtek is leading. And so far, we actually have not held a meeting at one of the quantum-related meetings. That will happen hopefully sometime next year. Let's see, so agenda, administrivia, blue sheets going around, note taker we have done, scribe, agenda, if anyone has any comments at this point on the agenda, and the RG documents. We have 3 active drafts which we will be looking at. There's a 4th report there under RG business on QKD in SSL, and then I hope to run an open mic discussion for about 20 minutes or so. I spent some time last night and this morning updating a list of proposed topics for discussion, including whether or not we want, whether and how to move from proposed RG to RG, perhaps in Vancouver, suggestions for the next meeting date, advice from the floor on what and how to move our existing IDs to RFCs beyond whatever gets discussed about the documents themselves. And a couple of things one thing that came up on the mailing list just recently, denial of service attacks and integration of quantum internet services into the larger internet. There's no documents associated with that, but it's been actively discussed on the mailing list. If anybody has any comments during the open mic section, and also potentially a list of things to take on next, including suggestion from the mailing list on QKD architecture, or how to integrate QKD into the internet architecture. Naming and addressing of nodes came up early this year and has sort of gotten pushed aside as a discussion issue. Routing, quantum resistant crypto or PKI, and how to integrate that in, and security of the networks. All of these things came up earlier. So any suggestions, comments, questions on the agenda? Colin.
Hi, Colin Perkins. Just a note that some of the security working groups have quantum resistant crypto things, so make sure you're talking to them. Yes,
absolutely. The point would be the point of doing that in this venue would be to coordinate with them rather than have it go on in some way that's completely unrelated to IETF or IRTF. Thanks. Anything else on the agenda? The details of these specific items we can talk about in the latter part of the meeting itself. If not, first item up, Wojtek, draft IRTF QIRG principles. Let's see, you want to use this device? Yeah. All right, let me find the slides. Architectural Principles of the Quantum Internet. How's that?
Thanks. Hello. Okay. Hi, everybody. I'm going to talk about the work we've been working on the draft on the architectural principles of the quantum internet. As a brief recap, the first version was prepared and presented at the IETF in Prague in March. The main motivation for bringing it forward to the QIRG is to address actually one of the charter points, which is that to create an architectural framework delineating network node roles and definitions to build a common vocabulary and serve as the first step toward a quantum network architecture. And also, because the IETF is mostly people who don't know quantum mechanics at all, also to create a good starting point for people with no quantum background and kind of serve as the document you would read if you want to kind of understand what the challenges, problems are, and how do these things relate to the other work done in the IETF. The draft was adopted at that meeting. After that first meeting, I received a lot of comments, but the first round of comments was actually mostly either editorial or there were very vague, open-ended questions. It would be good to add this, it would be good to do that. So towards in the run-up to this meeting, I eventually organized some web calls through which we started actually going through these open-ended questions as a group. Rather than just me hiding away and trying to do all that. As part of that, I've set up the work on GitHub. It's convenient because it lets us share updates at a finer granularity than Data Tracker and do convenient diffs, and people who know GitHub know how to navigate it. But we're still doing all discussions through the mailing list. Essentially, I don't think there was enough inertia to move too much to GitHub. So a brief overview, I will actually go into more detail for those who don't actually know what's going on, but a brief overview of the changes since March. 3 new authors have been added, multiple small editorial changes. There's been update to the security stuff in the draft, and we've reworked 2 sections to essentially better address the concerns and provide a better understanding of the situation to people with a networking background, but no quantum background. For those who have been monitoring the mailing list, not all contributions have been reflected that have been made in the run-up to the meeting, essentially because busy in Penang getting sunburnt on my shins instead, rather than incorporating changes. So here's a list of the things I still, as a group, we still need to do. Rod has provided quite a lot of comments, but I only incorporated some of them and to do with section 4 and 5, but there's still quite a lot to go through. There is a subsection written by Sarah and Marcelo about link generation, which I have to incorporate still. And there's a pull request on GitHub from Patrick about encodings, which I still have to actually look at. So what were the major updates? The major updates were to do with security in quantum networks. It's kind of actually an interesting thing, security, I think, because we do kind of have a clean slate, and it's kind of not a secret that security is kind of poor on the non-quantum internet. So it would be good to get it right, especially since one of the selling points of building quantum networks is better security. So I think it would be good not to kind of delegate it to a second-rate question, which is too easy to do. And there were 2 updates to Section 4. Section 4 is essentially about kind of a more clear description of what's the life cycle of entanglement in a network, entanglement being the key resource in a quantum network, as it created, used, and delivered. And update to Section 5, because essentially what was not clear to the non-quantum audience is that a non-quantum network, which is what we call classical network, is actually a key part of a quantum network. The quantum network won't exist in isolation. It will heavily lean on and use the networks built we already have, like the public internet. And hence, we will have a dual quantum classical data plane. So what was the update to security? Essentially, the point is, in a quantum network, user data does not actually enter the network. The network delivers so-called entangled pairs, and these entangled pairs are used to teleport the user data bypassing the network. However, there are still security considerations because you can leak information, which could allow a malicious third party to intercept your communication. And there's obviously also questions about authenticity, integrity stuff. However, most crypto applications and most security applications essentially do that kind of security at the application level. So as long as the quantum network kind of satisfies the model of a entangled pair source, the network itself should not tackle at all the questions of integrity, confidentiality, and authenticity. That's up to the application. And an interesting question is, because it's fidelity, which is the quality of the entanglement you deliver. If it's less than 1, it kind of means you've leaked information, but because it's not actually used, it doesn't mean your communication is now less secure. It actually just means that your applications will have a lower rate because they have to abort more attempts than they would otherwise with better entanglement. However, so that was just about end-to-end security, but there's also obviously a lot of security in the network. And as actually Rodney mentioned, one question that kind of came up but is not actually considered at all yet are things like denial of service attacks and kind of network level threats, which, as far as I know, are completely untouched. I've put a point that I think it's likely will piggyback on classical solutions, but I actually have no idea. And there's a question mark of whether this should actually make it into this draft. Another major update was an update to the lifecycle of entanglement. It's rewritten to clarify the whole process for the purposes of the reader with a networking background, but with no quantum background. Again, when I wrote the draft first, I kind of wrote it from my perspective, which is a physicist perspective with networking knowledge. But that's not actually the audience we're targeting. So based on the calls, it was kind of a lot of issues became clear as to where we should clarify, etc. So as part of those changes, so first in the updated section, we illustrate now the challenges to do with what's the main challenge in a quantum network. And essentially in a quantum network, some major challenges are the fact, such as the measurement problem. In a classical network, you can look at your packet, you can actually read the headers. You can read even the user data if you so wish. You can't do that in a quantum network. When you do, you destroy your data, your entire state. So you cannot do that, which kind of already in that, it makes copying difficult. But what makes copying really difficult is the no-cloning theorem. You cannot actually copy anything in the quantum world. Copying is basically how you do networking, and you can't do that in quantum networking at all. It's just physically impossible. It's not a technological limitation that is actually key to know. This is actually a fundamental limitation of quantum mechanics. And the last challenge is fidelity. So in classical networks, when you deliver a packet, you basically either deliver it perfectly or you don't. So you drop it by checking the checksum. And if it doesn't match, you drop it. And quantum networks, delivering a perfect state is incredibly challenging technologically, potentially impossible. But also, most applications don't actually need perfect states, so they can actually get away with imperfect states. And the key point to note about that is that imperfect states means you can deliver them faster. So there's a trade-off between the quality of state and the rate which you can deliver things. However, as I point out below, it kind of makes these kind of things makes transmission difficult. And the point is, rather than in a classical network where we send bits from source to destination, we were not going to be doing that in a quantum network. We're not delivering a qubit from source to destination. Instead, we will distribute entangled pairs of particles to the two endpoints, and the two endpoints are then free to do what they please with those entangled pairs. And one of those things they can do with those entangled pairs is quantum teleportation, which is data transmission, quantum data transmission. And the life cycle of entanglement, roughly like what it proceeds, basically first you generate entanglement on a link. You generate a pair on individual links on your path, on all of them, potentially in parallel. So now you have an entangled pair on every link on your path from source to destination. And then you combine them using a technique called entanglement swapping, where you can actually combine neighboring entangled pairs to create a longer veil pair. And at the end, you want to deliver that pair, those two qubits that form that one pair, to the endpoints, who are actually going to then use it for things such as quantum teleportation. But before you deliver to the endpoint application, there's three things you have to consider. Pauli corrections. What that effectively means is you have to either deliver always the same next pair to the endpoints, or because there's one of 4 possible pairs that can be delivered. And so you either always deliver the same one, so essentially you have to do the Pauli correction to bring it to the same state, or you actually tell the end nodes what you have delivered to them. Another key important feature is that the 2 end nodes must be able to identify which qubit of theirs belongs to which bell pair, so they can coordinate actions on the same entangled pair. If that information is lost, having just one qubit of a pair but not knowing where the other endpoint is useless. You might as well just throw it away. And another important point is you need an estimate of the quality of the state that you have been delivered. If you don't have an estimate, basically you then just have to rely on other higher level processes, which means that your performance will degrade because you can't optimize. Basically, you can't ask the network for what you actually want. So just to highlight with an illustration of what I mean. So if this is like a 3-node network, A, B, C, you'd first generate an entangled pair between A and B and C. So here's one entangled pair X1, X2, and another entangled pair Y1, Y2. This being a qubit, another qubit, Y1 being a qubit and Y2 being a qubit, squiggly line denoting entanglement between them. An entanglement swap basically takes X2 and Y1 and performs some operations on them, and you end up with an entangled pair that spans from X1 to X2 by performing only operations at node B. You do have to send some classical bits between from B to either end node, so it's not entirely done just by B. There needs to be some coordination at a higher level as well. So that was about the life cycle of entanglement. Other work that was done was about the network model. Effectively, what does the network look like? Because that's actually a big question raised by a lot of people from a networking background. And essentially the biggest question was biggest confusion was are we using qubits to encode header information or not? And the answer is no, we're not using qubits to encode header information. So what are the actual challenges? So I'll first illustrate the network model by illustrating the challenges we have when building quantum networks. Number one being there is no equivalent of a payload carrying packet. In a normal network, we're used to having payload and a bunch of headers attached to it that tell the network what we're going to do with it. This is not possible in a quantum network. It kind of resembles also transport networks, where you can have just optical networks where you can't actually read the header data. So there are some similarities over there. There are also many differences as well. An entangled pair is only useful if you actually know where both qubits are. So one of the key roles of a network is actually keeping track of this information. You can't just send a qubit one way and another qubit on its merry way and hope for the best. You actually have to know at all times where they are. Actually, not at all times. I'm not going to be that strict. But when it's delivered, when you actually want to make use of your entangled pair, you do have to know who and where holds the other pair and have to be able to identify it unambiguously. Another key difficulty is that generating entanglement requires temporary state. When you receive a packet in a normal network, you kind of just look at its headers, look at your routing table, and you throw it out another output port. It's kind of a bit more difficult in a quantum network because your qubits arrived separately from the control information. You have to maintain state to correlate their control information with your qubits, and vice versa. So therefore, there's a bit of a disparity. Again, some similarities to GMPLS networks. However, generating end-to-end entanglement is actually a parallelizable operation because since we're not transmitting user data, you can actually just generate all these individual link pairs in parallel. You don't have to wait to generate the next one, only after you're done with the first one. So it means quite importantly that you're going to be doing a lot of things in parallel. And it's quite important for optimization purposes to actually do these things in parallel. And here's the point that kind of just to really drive it home, classical communication is necessary. Quantum networks will lean very heavily on the existing classical infrastructure for two reasons. Number one is you need to be able to communicate classical bits of information between the various nodes. One example is in an entanglement swap, you actually have to tell the next node what was the result of your operation? Because the result of the entanglement swap operation is actually a number between 0 and 3. So there's 4 possible outcomes, and that has to be sent to the receiver, to their end. And this has to do with the 4 possible entangled pairs that you can create. And another reason why you want classical communication is simply the same reason why you want to have that in a normal network. You want to do routing, you want to do signaling, you want to be able to set up circuits, you want to do a bunch of management stuff. And there's no point in doing that with a quantum network. We already have a bunch of stuff that works. Again, I'm going to go back to the example of GMPLS because there's a lot of similarities. And actually, there has already been work on doing some quantum with GMPLS. Also added, actually defined the elements of a quantum network. A quantum network will consist of quantum repeaters. Quantum repeaters are effectively the devices that perform the entanglement swaps. They're the kind of way we get past the fact that we can't amplify signals. I've pointed out that they're automated and controllable because, for example, if you want to build a long link, you can't just lay down a long fiber because eventually you lose your signal, and you can't just put small amplifiers or something along the way. You basically have to put full quantum repeaters. But these quantum repeaters will probably be fully automated in the same way you just have a simple switch, layer 2 switch or something. I distinguish quantum routers from quantum repeaters to kind of distinguish nodes that have a control plane. So a quantum router would still be a repeater because it's capable of performing an entanglement swap. But if it has to make decisions such as well, I actually have more than just 2 links. I'm not just going from one side to the other side. I'm actually, I can make decisions. So these kind of repeaters will have a control plane. And there's actually distinction between these two. You will have automated nodes, fully automated nodes, simply performing repeating operations. And you will have essentially nodes with a control plane. I distinguish end nodes because end nodes can be simpler than a quantum repeater. They don't have to be able to perform an entanglement swap. They don't even need to have a quantum memory. They can literally just receive their end of the pair and measure immediately. So there's actually smaller requirements in the end nodes than on the intermediate nodes. There may be non-quantum nodes to perform management tasks, say a centralized controller. And obviously you will have quantum links and classical links to kind of, again, highlight the fact that you have 2 data planes. You have a quantum data plane and a classical data plane. A kind of an illustration of what it all looks like. You will have applications at the top communicating with each other over a classical channel. The applications will run on end nodes, and these end nodes will be connected via a physical link at the bottom. Just to illustrate, that physical link will most likely also be the quantum channel through which they distribute their qubits. But an important point to make is they will also need a classical channel to communicate the control information I was discussing. But that classical channel doesn't have to be essentially the same physical link as the quantum channel. It can be completely separate. They can share. I'm pretty sure there are technologies to share quantum and classical information on the same fiber. There's many ways of implementing that. But that's kind of not part of this draft. Looking forward, what else is there to do? I'm going to finalize the updates to sections 4 and 5 based on feedback from the last call from 11th of November. I've mentioned there's a few pipeline changes still need to be incorporated. And another work to do is whilst we don't really tackle too much physical layer stuff in the draft, it is very important to highlight what are the difficulties brought into the architecture based on physical constraints. Essentially, one of the biggest constraints is memory lifetimes. You can only store qubits. Currently, technology lets you store qubits for very, very short amounts of time, which require very strict timing controls. And then, essentially, the purpose of the draft was to kind of outline the goals and principles of how would you design a quantum internet, and that's kind of still untouched. I've got some feedback on that, but that will essentially, now that we've kind of laid down the foundation for a better understanding of what's going on, to kind of now move on to the goals and principles. And I put down network level security with a question mark. It's a good question. Should it end up here or should it not? Should it have a separate, should be separate work? I don't really want to relegate security to a second-rate concern, because it's actually, since these quantum networks are built around the idea that they're going to be more secure, it's kind of important to tackle any concerns that might arise. And that's it from me.
All right, so that was actually about 19 minutes out of our 20 minutes scheduled for this. But I only have 60 minutes of agenda items and we have a 90-minute session, so it's totally okay by me if we run over on this for however much Q&A we have, because I think this is the single most important item we're actually working on in the group. So questions from the floor? And give us your name too, please.
Okay, sure. Nalini Elkins. Now, I'm just wandering into this slowly, but and I will tell you that I have had a very misspent life focusing on measurement and diagnostics. And so I kind of get the jitters, you know, when you say you can't measure anything. And having said that, the success of all this depends on a good management system. So I'm just curious, you know, because I was kind of going through and thinking, well, what are the parameters one would need for this good management system, and what can be thought of, you know, I mean, what can be measured, like number of, like where qubits were at a particular location and how many you did, or, you know what I mean? I just want to get your thoughts on all this rambling.
Yeah, so the examples you've given like are good examples. You can keep track of essentially like, for example, the entangled pairs come with their IDs. So when these entangled pairs are generated, even on a link, they come with an ID. So you can keep track of the ID.
Well, comes with means we have to build the protocols that maintain. Right?
Yes, that is true.
That's our responsibility here in this room, right? Because the physicists don't know how to do that.
Yeah,
right?
One could have an identifier.
Yeah, so,
Yes.
so you allocate an identifier to entangled pairs, and you can keep track. And actually, one part important thing to actually keep track of is which entangled pair have you entangled swapped with which entangled pair, because it's actually critical in the end-to-end delivery. So that's one thing you can definitely keep track of. You can keep track of failures to generate on a link. You can keep track of how many have successfully generated. The entanglement generation, it's kind of still missing from the draft because it's one of the pipeline changes, but actually the entanglement generation on a link is heralded. So you actually get a notification when an entangled pair is generated. So that's something you can keep track of information of. And actually, there's also a lot of other information. Mostly this other information is kind of metadata, such as when did your pair arrive? When was your pair successfully generated? So which time bin? When did you perform operations on it? What result it came out? Was it delivered successfully? And so on. There's basically anything. We can keep track of anything apart from, we don't actually need to measure the qubit. The qubit actually doesn't carry anything interesting to the network. The only thing we cannot measure at all is effectively the fidelity. We can only have an estimate of the fidelity. There really is no good way, I think, because to measure fidelity, you would have to repeat the generation multiple times and then measure it multiple times, and have to make sure that it's the same, that you've performed the same thing many times. So that's the only one thing that I think would be difficult to measure. Everything else is fine.
Yeah, I mean, down the road, if we get into like what would be the things, I mean, if the group thinks that's an interesting topic, I'd certainly be interested in working on something like that.
Hi, Dave.
Let me take a process interrupt for 1 second. Blue sheets, if you have not signed the blue sheets, please do. There's one up here in the front. I'm not sure where the other one got to. Okay, Dave.
So the model here, which is great in some ways, says that there are end nodes for which where computations and applications run, and then there are repeaters which allow you to build longer links and more complex topologies out of the communication channels with both the classical and the quantum. So something that's happening in parallel in this community is something called computing in the network, where intermediate devices in the network that we classically think of as either just repeaters or switches are also doing computation. So I'm curious, what happens to this model if the things that you're calling quantum repeaters are actually quantum computers? This internet thing, this quantum internet thing, is actually sort of a way to distribute a quantum computation.
It's a good point. I think Rodney actually often calls the problem of distributing entanglement as a distributed computation, but it would be a distributed classical computation to deliver the entangled pairs. So
the only operation on a qubit at one of these intermediaries is an entanglement swap.
yeah.
Well, there
of other qubits there that is used to actually perform some stage of
Yes, there are actually multiple choices of operations that can be done besides just the entanglement swapping, most having to do with error management. But you're exactly right. And as Wojtek said, I often call this really it's not store and forward. Building an end-to-end connection is a distributed computation. And in fact, right before the meeting started here, I was talking to Aaron Falk about the coin work, and I really think there's a lot of potential, at least intellectual synergy. I'm not sure if there's actual technological overlap or not, and that's something I'd love to pursue with the coin people, you and Eve and whoever else.
Hi there, Niels Meurer. So I had the pleasure to play around a little bit with Qiskit, so the IBM quantum computing hub. And so what I did was initialize 50 qubits with a 0, perform a no operation, and measure the results. And I think in 50% of the cases, at least 1 qubit flipped. So without performing any operation, right? So what do you do about this if you're talking already about routing and maintaining a state? What do you do about bit flipping?
So there are quantum error correction codes. They're not really considered in the near term because they have quite high resource requirements. However, it all actually kind of comes under this guise of fidelity. So fidelity kind of also encodes potential bit flips, and essentially how close you are to your desired state. And effectively what it means is that your end-to-end application, which is performing some security protocol, will effectively detect and abort transactions that it detects that it leaked too much information into the environment. So that's how it's going to be dealt in near term. In the future, there will probably be proper quantum error correction codes implemented. There's also the idea of distillation, but I don't think distillation would solve bit flips. It's all about like delivering a better pair. But yeah, error correction is kind of a more long-term concern, and we deal with imperfect states as well as what we have now. It basically just reduces the rate with which you can deliver at the end.
All right, thank you.
So the distillation that Wojtek just mentioned is, in effect, it's error detection as opposed to error correction.
Okay, name is Paul Mushane. I have a question and concern about measurement, because is there a danger that when you try and measure entangled pairs, you may decompose maybe a quantum system now to a classical system, and therefore it will now behave more like a classical system?
Yeah, that's why you want to you will want to avoid measurement in the network, except during the entanglement. One part of the entanglement swap is actually measurement, so you will want to measure it then. But in that case, the measurement is done in a way that it actually transports entanglement rather than destroying fully. Essentially, what you're concerned about is like reducing your system to a classical system is effectively decoherence, so interactions with the environment. It happens, and currently it's taken into account by the fact that your fidelity degrades, and you're going to be delivering imperfect entangled pairs to the end nodes. Does that answer your question?
Yeah.
Okay.
Let's close off the line with the two people who are here in line. Both of you are there. Fine, but let's end it there, and then if there's more, we can do it in the open mic section at the end.
We have to stay together.
Entangled, yeah. Okay, no, well, Diego Lopez, I'm the voice that claims in the desert about the physical stuff and all the like. No, seriously, what I think, and I'm trying to, I'm taking this moment just to try to clarify a little bit what are my thoughts. We have a conversation pending, but the point is that I think that we are running too fast in following the same analogy with the current network model or the current classical network model, in the sense that we're assuming that there's going to be a physical layer. We need a physical layer. We live in a physical world. That's but then is about talking about links, talking about network, talking about application. I think that we are running too fast because we don't have right now the operational experience of connecting several quantum computers and see what happens with them. And probably we could step back a little bit and start thinking about, and probably the physical analogy is not good because it's misleading as well, in terms that when we're talking about this, what we have with an entanglement, we could be talking about, we have a channel, we have a circuit, we have something that connects two or several, because theoretically, my understanding is that you can connect at the same time with You don't need pairs of entanglements. You can have an entanglement with several ends. Thinking about starting that so far what we know is about building entanglements. Well, that we know what can be done is building entanglements and calling them a whatever. Call it whatever. Probably I would avoid the term link or whatever it is equal in the classical network case, and try to elaborate over this. That was my point. Probably I was not clear on the list, and this is why I wanted to insist here. It's about trying to avoid over the excess of analogy.
I'm sorry, did I get your name? I'm sorry, did you say
Diego Lopez? I work for Telefonica Research.
Thanks.
I'm still actually, because you say avoid analogies with the link, but we will need a link.
Avoid, no, not to the link. Avoid analogies with the current network model with the 7 layers, the link, the physical, the link, the network, the transport, etc. Because probably the number of layers, the layering, etc., will be different.
Yeah,
simply that.
Actually, I actually agree with you, and kind of. That's why on the calls, I actually have resisted trying to put an explicit definition of layers into this draft. There is work in this community about layers, but that's fine if it's separate because we kind of need to start understanding these things. But I actually did try to explicitly avoid talk about layers. We did start talking about responsibilities, which people try to relate to layers, but I really do want to avoid defining a stack in this draft completely. Yes, no, I agree with that.
Okay, I'll hold it. Marie-Josée Montpetit, I'm actually...
Your name, please?
Marie-Josée Montpetit.
Thanks.
I'm actually the chair. I'm actually the chair or the co-chair of this COIN group. And it's great that we're talking COIN here because in COIN we thought about you guys. And the idea is that we had comments from the IAB about putting security in our systems, especially when we start putting computing elements. And actually we thought a homothetic security, which is not very feasible without some form of quantum computer. And I was wondering what were your thoughts on future of security systems inside the network now that we have this type of communications?
I have not thought much about security apart from, so you mean about security of the in-network nodes, computing nodes?
Yeah, and also of the overall infrastructure that needs to be secure if we're going to have access to the information while it's in transit, because a lot of people are developing more and more end-to-end encrypted system. And first we have to have trusted nodes in the center. But if there's strong encryption, well, it takes a while to decrypt them. So frankly, it's not a really great idea then to put computing because we'll never get access to the data. And we started thinking about homothetic signatures and security. But again, you need very, very high level of computations for this. And I was wondering in your system, again, what you're thinking about, how is this going to be dealt with, both from, I would say, the traditional computation where you start, like Dave said, to have quantum computers in the system, but also even for your thing, how are you going to deal with security? It's more of a comment, maybe, than a question. But we've because we are putting computation in the network, we are very much involved in thinking about what's going to be the next generation of this, and maybe it's here.
Yeah, so it's probably the only security that I'm aware of that we've thought about is end-to-end between applications. And I have mentioned that we have not thought about any security in the network yet. I don't think anybody has thought about any security in the network for quantum stuff, maybe a tiny bit somewhere else, but that's something that Rod has suggested for the open mic. So
okay,
I would say you are much closer to helping us than we are to helping you.
Well, let's agree to help one another then.
Yeah, but I will actually disagree. So we actually have one paper, the title of which is the network impact of hijacking a quantum repeater, that actually looks at whether or not the hijacking of an individual node in a network is actually fundamentally different from the hijacking of an individual router in the internet. And we found, yes, but it's possible to mitigate it. I think I actually mentioned that paper on the mailing list, but maybe you missed that one. All right, let's finish this discussion here now. If we have more to talk about with this, we'll still have some time at the open mic, I hope. Let's see. And now the next task is actually challenging for me technically, technologically. Next, we are to have a remote presentation from Axel on the link layer protocol. Who wants to show me how to run the Meet Echo on this? Or as how do I bring it up so that Axel can run this run the presentation remotely here? Aha.
Can you hear me?
Let's see. So if I just, what do I have to do to unmute him? This? Axel, you with us?
Yeah. Can you hear me?
Aha. Let's see. Do I run the slides from here? Is that what I do? All right, Axel, you're up.
Okay. Let me know if is this sound good or
Speak louder.
speak louder.
Yes.
Can you hear me now? Is this a good talk? Okay.
More is
so-
always better. That will do.
Let me know if it's not good enough, but I will try to speak loud. So my name is Axel Dahlberg. I'm at QTech in Delft, also with Stephanie Wehner. And I will give a brief presentation on our draft, which is called the Draft Dahlberg LL Quantum, which you can find with this QR code here. So this draft is on the link layer service. And what's the task of the link layer service in a quantum network? And what would an interface be to this link layer service? And I would like to just briefly recap what our view of a link layer service is and what this draft is about, and also what changes have been made since the last meeting. So just to be very clear, so this is about our definition of a service, so not of a protocol implementing this service. And what is then the task of a link layer service? So depending on how you want to formulate it, in some way or another, in a classical network or non-quantum network, the goal is to send a message, a classical message from one node to another. And you might think that in a quantum network, then the fundamental task would be to send a qubit from one node to another. However, this is not the most fundamental operation, which Wojtek mentioned. The more fundamental operation is to generate entanglement. And the reason for this is that when we have entanglement, we can use this to send qubits through teleportation. So in our view, the task of a link layer service is to generate entanglement between adjacent nodes in the network. Let me just maybe check in here if this is working and whether you can hear or understand me. Just give me a...
I can hear you. Let's see. So, but you'll have to tell me when to change pages.
Yeah, okay. You can, next slide, please. Okay, so the task of the link layer service, as I mentioned, is to generate entanglement. It turns essentially a physical layer, which can make entanglement generation attempts that might fail with some probability, into a robust service of entanglement generation. What was also mentioned in the previous talk is that the link layer service will return an identifier of this generated entanglement that can then be used in the network to track this entanglement and for nodes to agree on what qubits are entangled. So as I mentioned, this is about the service, but if you want to read about a protocol that we propose that provides this service, you can find this in a paper from ours, which is on the archive, which we presented also at SIGCOMM this year. Next slide. So in brief view, how would this work? So in our view, the link layer service, how you interact with this is that you ask it to create entanglement with what we call a create message. This create message contains a few different things, and I won't go into the details now. But for example, you can specify what is your required fidelity. And the reason for this is that there's usually a trade-off, as Wojtek mentioned, between fidelity and the generation rate. And not all applications requires perfect fidelity, because some of the noise can be corrected classically in post-processing, when, for example, generating key. Another type of argument in this create message is the type of request, and we currently envision two types of requests, where one is to create the entanglement and keep it in memory at the end nodes. This is then different from creating entanglement, which is measured directly to generate correlated classical bits, which can be used for example, key distribution or quantum key distribution. And how this then works is that this create message is supplied from one of the nodes, and later when entanglement is generated, an OK or a signal is returned to both nodes that now there is entanglement, and this is your qubit that's entangled. And I should maybe mention that in this draft of our link layer service, we've defined basically what goes into this create message as fields in the headers, and we specified the bits of these headers, which might be confusing and cause some confusion in the sense that I think this is not generally the way to maybe define the interface to a service. And there's been some suggestions, so maybe next slide, from various people. And I just wanted to briefly mention that we also have a GitLab repo with this draft, and there are current issues there. And for example, one of these issues is that we maybe shouldn't fix, for example, the number of bits in these fields of the headers, but maybe we can instead use a type length value message to make it not as fixed. Okay, but what has changed since the last meeting? So next slide. So this is the new header, and I just wanted to briefly mention what has changed. So next slide. One thing that's changed is that in this create message, one can specify how long are you willing to wait before you receive your entanglement. Because perhaps some node cannot wait indefinitely. And we earlier had just a single field which specified the max time one is willing to wait. There's now a new field which specifies the time units of this max time. So you can specify a maximum waiting time in essentially microseconds, milliseconds, or seconds. So this is one of the change. Next slide. The other slightly bigger change.
Axel, we have a question from.
Just jump in really quick because we faced the same problem somewhere else. Look at something called time TLV, which was actually done for Manet a while ago, which is a TLV encoding mantis and exponent. So you can choose between short times with high resolution or long times with low resolution with one data structure.
Dave, name for the record.
Oh, Dave Oran. Sorry, I said it last time. So it's probably a better encoding than a fixed time encoding where you have to choose your poison once.
Great. Thank you very much. That's very good to hear. I will definitely look into that. So the other thing that changed, which is slightly technical, is that, as I mentioned, there's this type of request where you want to generate entanglement and you want to measure it directly. Now, in quantum mechanics, you can measure in different bases. And depending on what your application is, you might want to measure in different bases, and you might want to measure in a random basis. So what has now been added is more possibility to define what basis you want to measure in for both the requesting node of entanglement and the remote node, and also how to sample these random bases by specifying essentially a probability distribution. Next slide. Oh, so I should have said next slide earlier, probably, but this was about the time units. Next slide, yes. So there are now new fields to specify the probability distributions and the bases you want to measure in. Next slide. So at the GitHub repository, there's, I think, currently 10 open issues, mostly pointed out by Bruno Reisman. For example, about this type length value messages. And also something that came up earlier is about the scope of a remote node when you specify who you want to generate entanglement with. And we're very happy for contributions about this. So if you want to contribute, either use the mailing list or go to the GitHub repo and submit pull requests or issues. And I'm very happy to discuss this.
Okay, let's try to keep the questions and answers to about 3 or 4 minutes for this one. Diego?
Yeah, Diego Lopez. Just a suggestion again about the analogies, etc. What I can understand, we call this a link, though I would prefer something different because to avoid the analogy. But well, let's keep it as a link. What you're mentioning here, what you are sending when the what you call here headers, are more, I would call them the control messages. I mean, you're not putting a header plus a payload with data, right? It's just a header. It's more like you are communicating, more than a service, it's a control plane communicating to a data plane or to a quantum data plane. I would talk here about control messages or control actions or something like that, because it would be clearer to understand for those of us who are more used to the normal network environment, and I think it describes better the goal of what you were showing.
I like that suggestion. Axel?
Yeah, thanks.
Sorry, Dave Oran again. So there seems to be a missing link here in the sense that the architecture document talks about the really nice fact that you can do a lot of things in parallel. But this seems like you have a very serial, make one call, create one entangled pair, make another call, send another message, create another entangled pair. So I wonder if the protocol really shouldn't be some type of parallelized, such that you can say, create me 75 of these entangled pairs, perhaps all with the same characteristic, because you're going to do the same thing with all of them. So I'd give some thought about, given the fact that we have the opportunity to do a lot of parallelization, designing a protocol that seems to be biased to doing things serially.
Yeah, so that's a very good point, and I didn't go into the full detail of this draft, but this is definitely something that's already in there. So one of the things you can also say in this create message is how many pairs do you want? So you can say, I want 1,000 pairs and I want to measure them directly to generate key. You can also, it's not sequential in the sense that you need the OK message before you send another create. You can submit multiple creates and this will be stored in a queue essentially. And you can do various scheduling of these create messages. Yeah.
Hi, Wojtek from QTech. Just a clarification about what I meant by parallelizable operations. So what's parallelizable is, so over here in this draft, Axel's talking about an individual link, whereas if you have a multi-hop path with, say, 3-4 links, then you can definitely parallelize those 3-4 links, where you have 3 or 4 fundamental link pairs generated at the same time, rather than hop by hop. So that's one thing. So when I said parallelizable, that's what I meant. Although I do also get your point, I guess, that on the individual link you can also parallelize.
Okay, Paul Mushene on the record. I went through the draft, and there is actually the number field on the link there, and it has been set to 16-bit. So the number of entangled pairs that can be generated is around 65,536. Is this a hard limit? And I just wanted to know the design decision behind this, because is this been set because maybe of a physical restriction in the number of entangled pairs that can be generated?
No, and I think, no, it's not. That's I guess the answer. And I guess this comes back to the question that it's maybe not the best choice to now set the length of these fields, and it might be better to move away from a fixed bit length of these fields.
this is not me, it's a question from Java. I don't have the name because I have asked for it and it's not yet here, but well, the question is, Federico Santandrea is asking whether it could be possible or useful to generate entanglement all the time and distribute pairs as needed.
That's a good question. So why we didn't go for this approach is that at least in some physical systems, it's not so advantageous to do this. And the reason being, for physical considerations, is that in some systems, for example, the system we have in Delft, whenever you try to generate entanglement, you produce some noise on your memories. So you would like to not unnecessarily try to generate entanglement if there's no need for it. So that's the motivation for not always trying to generate entanglement.
Okay, with my individual hat on, I want to ask one quickly. So, Axel, the new additions you talked about with the requester getting to specify the choice of measurement basis when you're actually measuring the qubits out directly, does that belong as part of the link service, or should that be end to end?
Well, so this is for basically, I guess, if there's an application running directly on the link to generate, for example, key. And the reason why this is part of the entanglement generation request and not something you do after the entanglement is generated is that when you measure directly, you can generally go faster because you don't have to wait for communication essentially to if there's a midpoint or a heralding station.
Yes, but my point is that I think that argument holds over multiple hops as well as over a single hop. So I would argue that belongs at a different level in the stream of specifications. That it should be part of the specification of the end-to-end service rather than part of the link specification.
But okay, I'm not sure I agree because it should still need to go to the link layer generation service such that it's known already what the measurement basis is when you try to generate entanglement. It could also come from higher above.
Okay.
I'm not sure. Yeah.
I'm not sure I agree, but let's
Sure.
call a lid on this.
That is more a comment than anything else. It comes from which is it's a number. I only have a number, but they say I agree with Ron that the measure immediately logically belongs in a higher layer, the transport layer, but I'm sure Diego won't like that name, and that's true. I don't like it.
Okay. Thanks, Axel. I hope you're hanging around. There may be more questions for you later.
Yeah.
Let's see if I can figure out how to turn you off.
Have a good rest of the meeting. Thank you.
Let's see. Good. Okay. See if this is going to work. So my own internet draft here. Let me make sure I can see a clock. On connection setup in a quantum network. So sooner or later, you're going to have to set up a connection from between a pair. So I've marked S and D on here, but that's really, rather than source and destination, it's really sort of initiator and responder in terms of setting things up, because we are talking about entanglement as a service rather than transmission as a service. If you want to go into some of the details of this, the slide set from Prague is a little bit longer. Let's see. So there are sort of four stages of the overall problem. One, of course, is first, of course, you have to select a path or a route through your network. You have to collect a set of information for planning the set of operations that you're going to actually execute at each of these nodes in the middle. And this, again, Dave, is sort of the distributed computation part of it. Then you have to actually do the planning of this operation, and then you have to convey the sequence to these nodes. And all of this is done in the set of constraints or assumptions that links are heterogeneous and that not very much is known about the links a priori. And at the moment, resource management or multiplexing is beyond the scope, but that's something we probably need to discuss. And so this draft is aimed at the collection and distribution of this information rather than the process of actually planning the sequence of operations itself, and is not specifically targeted at the routing itself. So each of the nodes has some information about its own capabilities, including the amount of memory that it has and the memory lifetime and its own local fidelities. It has a little bit of information about the links. It knows who its neighbors are. And as in OSPF or a similar protocol, we're assuming that it knows something about the topology of the local network with some sort of routing metric and where the gateway to the outside world is, but not a lot of detail about the other things. So for example, it does not have full information about every single memory qubit everywhere in the network. We don't think that that would scale. So the basic process is if you pick a path from the initiator to the responder. So at each of these nodes, you send a message across the path, sort of building a stack of information about the total set of resources that you're actually going to be using. And then that runs from the source and through the nodes A, B, C, D, E, F, G, H, I. Once that arrives at I turns around and sends that information and performs the actual planning of the entire computation. And it creates a stack of operations to be executed at each of these nodes, labeled with the node for it. And that entire stack is then sent backwards through the network, and each node progressively pops its own set of instructions off of the top of it. So it passes through D to C to B to A, and each one collectively gets what it needs in terms of this. Once you have that, you have distributed the set of rules for which each node's actually going to operate and during the course of this connection. Let's see. So there's a different diagram of what we're looking at there, and some of the distinctions that you have to worry about is you have to figure out where you're going to perform the entanglement swapping operations that Wojtek mentioned earlier, which order you're going to do things in. Are you going to apply some sort of error management scheme? Which qubits are you going to use? If there are long wait intervals, how long a wait interval is too high, and at which point you discard the state you've been working on, reset, and go back to the beginning. Those sorts of issues are the kinds of things that get established in these sets of rules. The details of those particular operations are outside of the scope of the particular draft we've written. All we've written so far is the messaging for how this process actually goes back and forth. Let's see. So that's a list of a couple of the challenges there. So first draft of this, the 00 draft, was just before the prog, and we got some questions on the mailing list around that point. Someone brought up the suggestion of segment routing as an alternative to this or similar thing. I'm not particularly familiar with segment routing, so if there's anybody who wants to bring this up and discuss it more, by all means, let me know. Diego wants to step in.
Not me, but I have a couple of colleagues that are working very heavily on that. I will ask them.
Okay.
Because I don't consider myself an expert there, but I think I can gather a couple of them.
Okay. Let's see. So, and just before the deadline for this meeting, I put up the 01 draft. The only changes that from the 00 draft to the 01 draft were really fairly minor. Improved the definitions of end nodes and repeaters, but those really need to be coordinated or reconciled with actually what's going into a Wojtek's draft. We improved the discussion of non-data teleportation uses of entanglement. Teleportation is the equivalent of forwarding, except that it's done in a very distributed fashion. But there are other uses of the entanglement as well, so there's a little bit more discussion of that in there, and a little bit of a discussion of multiplexing and resource management. There's nothing prescriptive yet, but just sort of a description of the need for it. I really kind of wanted to avoid putting that into this draft because I think it's a very big issue, and so I think it belongs sort of elsewhere, or at least as a follow-on work item. Diego?
Java.
Yes.
Again, it's someone that's, again, a number is number 976489352 at hulletconfmiteco.com.
Okay.
And says, I don't think segment routing is applicable. We'll send an email to the mailing list with details.
Okay, thank you. And a couple of people in the audience here have been making faces about it as well. It's not a universally approved solution, apparently. Let's see.
Bruno Reisman. It's Bruno.
It was Bruno. Okay. Yeah. Yes, Bruno has been very active and involved on the list on a lot of these discussions. So following on from the posting of the O1 document, and actually some of the stuff even going back farther, I spent some time digging through the mailing list to see what issues are still open. Probably the single biggest issue is actually the question of creating what's called multi-partite entanglement. So we've been talking so far about entangling two things across the network, and a service is point-to-point entanglement, which you would use for quantum key distribution or for sensor networks or distributed quantum computing or whatever. But it's also possible to actually entangle more than two sites or more than two devices. And that's actually, there are a number of uses that have been proposed for that. And so it was brought up on the mailing list as to whether or not this particular draft addresses that and whether or not it should. My own preference is that, yes, we should eventually address that issue, but we should not do it in this particular draft. I think we should do point-to-point first so that we have some understanding of what we're doing before we try to add that additional complexity. We are also, I think, much farther away from actually needing that in the field. And so of course, I want the architecture to support it, but I don't think we need to actually address that right now. Someone brought up the notion of a connection teardown, which I realized while digging back through the mailing list, and that's a good point. I wrote a draft on how you create connections, but not how you tear them down. Presumably, you'll want to tear them down at some point. Wojtek suggested moving from the terminology that we used for the rules themselves of being condition in action to being match in action. That would be okay by me. There was also the suggestion of separating the rule set definition from the distribution. And I do want this draft to focus only on the distribution and not so much on the rules themselves. But there is, in fact, a little bit of discussion of that inside. So we can go into some of the detail on the mailing list about what should stay in and what should come out as a result of that. Yes, Dave.
Just a quick comment on teardown. You have to have a justification pretty strong for needing it, because you can just do soft state timeout. And that has very nice properties because it recovers nicely if there's a network partition. You don't have to sort of remember state during a disconnection to reconnect it, only to be able to tear things down and throw state away. So I would say start with the notion that these connections are soft state timeout, and just get refreshed on a timer in order to keep them going. And unless there's some strong reason why you really need to recover resources deterministically with a explicit teardown.
That's a good thought. The set of resources that are going to be available in any network in the short term is a very limited set of resources, and so potentially we may want to recover that or include it in some sort of resource management scheme. But personally, I sort of agree with you. I would sort of leave it for sort of soft timeout. But at least incorporating that into the draft in some way, as this is what's expected to happen, I think would be a good idea. The other big issue was whether this is single domain or inter-network, and the draft as written is for a single network. My own proposed approach to the overall inter-network architecture is to build off of the recursive network architecture, which Joe Touch and others defined quite a while back. For classical networks, but is not sort of widely adopted at this point. But I think it actually suits quantum networks very, very well. So we have one old paper from about 10 years ago on that working on that. Let's see. And so those are sort of the issues of what we're planning on doing for that. And that's it for my draft. Any further questions? Comments? How many people have actually looked at this draft? 10 or 12 here in the room. That's pretty good. That's good. Thank you all for doing that. All right. If there's nothing else, then we'll go on to the next scheduled presentation, which is on the integration of OpenSSL in this. Hang on. All right. Question.
Something from Java.
Yes.
Frederic Grosans. I fear that focusing on point-to-point links now instead of considering multi-party entanglement for the start will freeze some assumptions.
Will what some assumptions?
Will freeze.
Will freeze some assumptions.
But I don't know if it is good or bad, but it's not implied in here.
Okay, point taken. I'm not sure I agree with the. I would certainly say that the multipartite is a substantially more complex problem, and I want to keep things as simple as possible and add complexity only when it starts to become necessary.
So that issue is actually entangled with a different issue, which is you're also assuming congruence between the classical and the quantum channels, as opposed to independent topologies for the classical channels and the quantum channels. So that, you know, for example, you don't have a way to optimally use a broadcast classical channel in order to manage a set of point-to-point quantum channels. I mean, one could design protocols that worked where there wasn't congruence between the classical channel and the quantum channel.
I think
there's probably an interaction between that and whether you want to do multipartite entanglements.
I'm not sure there's actually a direct relationship there. I do think you're correct that so far we have not assumed the existence of a classical broadcast channel, although I don't think anybody's actually written that assumption down. And I would like to keep that assumption. I do not want to assume a classical broadcast channel. We do assume that
I use broadcast as like that's the other extreme of completely congruent one classical channel per quantum channel. But there are many intermediary possible deployments, right?
Yeah, I would say
I'm fine with keeping the congruence for now, right?
We do have to have quantum communicate or classical communication between all of the classical controllers for each of the quantum nodes along the path, but there may be boundaries beyond which, you know, the communication between these two nodes never crosses a network boundary, or even the existence of nodes within a particular network may not even necessarily be exposed outside the network boundary. That's one of the issues we've worked on with the larger recursive network architecture. But for this particular draft, we're assuming an individual network, and that all of the classical control nodes can communicate with each other as necessary. Yes.
We'll close the chapter line when you decide. But so far, Bruno is saying that he says, I see a strong resemblance between this protocol and RSVP. RSVP has point-to-multipoint LSPs, which are similar to multipartite entanglement. And Frederic is saying, I think, like Bruno, that the adaptation to some multipartite entanglement distribution is not too complex.
Okay. Bob Braden I used to have an office next to Bob Braden. He was one of the sweetest humans on the planet. So I like RSVP. But, all right, let's go on to the next presentation. That's true. I never worked on the code. Is this a very big file?
It's 250 kilobytes.
250 kilobytes?
Yes.
Should have been there. All right, there we go. All right.
Okay, so the clicker.
Oh, sorry.
Right, so I'm going to talk a bit about integrating QKD into OpenSSL. Where does this come from? So on November 5th and 6th, RIPE Labs, RIPE NCC, organized a pan-European quantum internet hackathon where multiple nodes participated, Delft, Paris, Sarajevo, Padova, Geneva, Dublin, and Geneva was actually CERN. And the idea was to tackle various quantum internet challenges. I was one of the technical coordinators, and one of the challenges I proposed for the hackers was actually integrating QKD into OpenSSL. So if you actually want to look up what the challenge was afterwards, it's actually all on GitHub, publicly available. But essentially what I was trying to go over and kind of lay down in front of the hackers was that having the end goal was to basically open up a browser on one computer and run a server running some basic website on another computer, and actually have an HTTPS connection, which was encrypted using QKD over a simulated network. They wouldn't really give us the real network once they build it. But what was the motivation for the challenge? It's kind of like my personal irk with the way the state of quantum networking is today. It's basically we either talk at a very low hardware level, low level operations like entanglement swapping, link entanglement generation, gates. It's very, very, very low level. And then we also have the other extreme where we're talking about application protocols, but they're all like quantum cryptographic protocols with really complex mathematical proofs. And I, with a physics degree, I struggle to follow them. And to be honest, I just give up most of the time anyway. It's not my area of expertise. So I kind of wanted to bring quantum networks to a user level application, kind of raise the level of abstraction and let people to actually hack at a higher level than just, stringing together gates like you do in Qiskit or Q#, etc. Kind of open up the field to software engineers who don't necessarily have a quantum physics background. Because I spent 2 years as a software engineer in a company that was doing control plane protocols. And at that time, I kind of completely stopped thinking about physics and kind of learned that software engineers are actually a very creative bunch, and they're much better at coming up with like practical uses of various abstractions and stringing them together into something more powerful. So that's kind of what I wanted to open it up to do. And also just practically relate the hackathon to QKD, because QKD is actually a commercialized technology that already exists, and people actually do sell devices and make money. Well, whether they make profit is a different question. I have no idea, but they are being sold. So the challenge was built around an API that ETSI, a European standards organization, is trying to standardize. I don't think it's standardized yet, but they're working on it. I have a bunch of documents about it, and it seems they're in quite an advanced stage. The API is very simple. It has 5 functions, but there are really 4. Basically, you open a connection. You open your connection to your QKD device. You connect to the other QKD device. You get your key, and then you close. What does the flow roughly look like? The flow looks like basically on your server and the client, you open your connection to your QKD device through your QKD API. You use a key handle to essentially identify the session at the 2 ends. The key handle can be sent in the open to the other end. It's essentially just an identifier between the 2 endpoints. There's also a version where you can pre-distribute the key handle and you don't actually have to send it between the 2 ends. You initiate a connection between the 2 ends, and then you run a get key again and again, and then you close it. So that's roughly the API. And what were the elements of the challenge? There were basically 2 parts. One was to actually integrate this API with OpenSSL, and the other was to actually implement the QKD API in software. So basically there were people who actually understood the physics and wanted to implement a QKD protocol could do so and basically provide that API. Or people who wanted to just have an abstract API and actually do hacking on an open source repository of OpenSSL could do that. And that first part is the one I'm going to focus on and talk about here. So there was actually a team in Delft that attempted to integrate this QKD API into OpenSSL, composed of Bruno, Ivo, and Tim. Bruno actually has a very thorough write-up. If you follow this link, it's very thorough. It has a lot of background information about like encryption, about SSL, why quantum key distribution, and so on. It's not just about the project, it's also a very thorough background explanation, so I do recommend visiting it. It also has running code if you would actually want to try out this thing. Roughly, there are 2 ways of extending OpenSSL. Basically, OpenSSL provides a way of extending OpenSSL using what they call engines. They're basically a way for OpenSSL to offload some of the heavier computational functions onto hardware normally. So if you have like Diffie-Hellman protocol, you can actually offload some of the more computationally intensive stuff onto hardware. That's what an engine is for. You basically provide callbacks for those things to be done in hardware. Or you create a first-class key exchange protocol state machine. The other one would require, the first one doesn't actually require you to change anything in the OpenSSL code base. The second one does actually require you to change the OpenSSL code base. The team opted to implement an engine. They abused the Diffie-Hellman protocol. So basically OpenSSL thought it was running Diffie-Hellman, but really the callbacks were just doing QKD. What does the architecture roughly look like? So we provided a mock API in order to let one of the teams that actually implemented implementation of the API. So actually at the hackathon, they just had a mock, which just didn't do anything quantum. It just provided the API in a mock way. And then basically they had an engine, Diffie-Hellman engine built on top of the QKD API that would actually communicate with the OpenSSL library. So it would register callbacks with the OpenSSL library, and the OpenSSL library would therefore do QKD, thinking it was doing Diffie-Hellman. Difficulties and challenges. The engine actually behaved differently on the server and the client side, but the callbacks were actually symmetrical in OpenSSL. So that kind of was a challenge. In the end, the team actually implemented two different binaries, two different OpenSSL libraries. And also the design of the mock API was actually pretty limited because it was actually meant to just be simple, so that we didn't have to spend too much time implementing a mock API. But it turned out the design led to deadlocks when you use the engines because of the way the state machine worked. So they actually had to hack on the mock API as well. In the end, they did. There's actually running code on this GitHub link. The conclusion is OpenSSL is actually quite difficult to extend, even the easy hacky way of doing it. And actually something I didn't put in is I found this project quite cool. I saw a team working on it because we've done a few of these hackathons already, and very often people without a quantum background would spend a day or two just learning about quantum. How do you combine gates? What do they do, etc. Whereas in this one, they actually could really get on and actually implement an application, an end-to-end application. So I found that quite fun. So yeah.
Okay, Shoto Nagayama is speaking. So actually, I used to work on a similar project. So actually, 10 years ago, my target was IKE. So I'm asking a question. So do you assume a failure of QKD? So the QKD may fail due to EBUS dropping. Then you need some kind of a fallback or.
So the fallback. So the way the API was designed, I actually probably should have put a picture, was that basically all the complicated stuff about QKD was done below the API. So essentially you had the whole system connected to each other. It did all the post-processing, all the difficult stuff was done below the API. None of the difficult stuff was expected to be done above the API, but no, we didn't have any. So I actually don't even know what the API specifies it does if it can't get a key. I think it just blocks, I guess. So no, we didn't have a fallback.
Okay, thanks.
A couple of comments. One from, let me recall, I think is Bruno. Yes. Bruno says, I'm working on an implementation of BB84 in Python using the simulacron simulator. The quantum part is done, but I'm still working on the classical post-processing, information reconciliation, and privacy amplification. Once the Python implementation is done, I will translate it to C and integrate it with OpenSSL work done at the hackathon. I expect this work to be completed within a few weeks at most. Everything will be posted on GitHub. No. Well, no.
Oh yeah, I was just gonna highlight. So yeah, Bruno is the guy who actually led the team. So he implemented this hacker and stuff. So yeah, do follow it. I do strongly recommend visiting that website. His write-up is actually very good if you are interested in this project.
Okay, let's make this. Let's wind this up quickly because we've already burned almost all of our open mic time, and I want to give people.
I guess this is somehow equal to the open mic, but anyway.
Yes. Well, Bruno's opinion's important because he's the guy who did it, right?
Now is that's a question. I mean, I think that precisely when it comes to the fallback and all the like, is about identifying a set of proper cipher suites to be used in TLS. With OpenSSL. This is something you have not done yet, right? Or
not that I'm aware of.
No, probably it would be once we have this, or you have this more or less stable, it would be interesting to discuss about the cipher suites and even trying to standardize them. Why not?
Right. Yeah.
Well, again, Niels Meurer here. So I didn't reveal the employer that I worked for before. So I worked for the German Aerospace Center. And first of all, thank you a lot for bringing this subject up. It's the very first IETF that I attend here. So in 2013, we got a Nature and a Science article for already trying to run a BB84 protocol synchronized with a plane. So plane flying, the key exchange and the data encryption, everything done. So this is something that we're very much looking forward to coming out, because there's a huge project in Europe going on called the QCI, Quantum Communication Infrastructure. That's based on the QNet project, and I'm pretty sure you're also aware of the Meteos satellite project run by the Chinese. So I think this is a very important topic, and I think next time I'm going to be here with 10 more of my colleagues, hopefully working on that. So thank you a lot.
Sounds cool. That's exciting.
All right, we've got 5 minutes for open mic out of the 20 I had hoped to have, but I think all of this has been valuable so far. Questions? Anything related to the working group at all, or advice on running the working group, or advice on where we should go next? Someone should have something. Hang on.
Yeah, sorry for kind of hogging the mic. So I only have one thing to say. So one of the topics that reoccurs in the mailing list is multi-party entanglement, but there's also one more topic that pops up every now and again on the mailing list, which is the relation between the way we do quantum networks and MPLS, or more specifically GMPLS. There's already work actually done that did QKD and GMPLS, so there's actually even a publication. I think, Diego, you worked on that. So there's actually already work on that, and I think it'll be an interesting question actually to tackle as well in QRG, given that there will be MPLS and GMPLS experts in the IETF. So I think that's actually Bruno has also committed to work on actually adding an MPLS section to the architecture draft. So there's definitely scope for a lot of questions on how do you do these things, what are the similarities, what can we piggyback on, etc.
Other comments or questions? One in particular I want to bring up before we sort of finish here. The proposal that's on the table is to push this from proposed RG to full RG as of after Vancouver, which is the next IETF. We have not yet committed to actually doing a QIRG meeting like this in Vancouver yet, but it's very likely to happen, and I almost certainly will be there in person. Any comments or questions on Vancouver or becoming a full RG? People in favor of that? Any other comments or questions?
Well, we could have you like that. Sounds very
You want to hum for whether or not we should push for full RG? Okay, everybody who's in favor of pushing for full RG as soon as sort of feasible, let's hum. Sounds like consensus to me. Anyone opposed to moving toward full RG for this? Hum? Sounds like consensus to me. Any other questions, comments? If not, we'll end up about 90 seconds early here. See you all at the social and/or at the plenary tomorrow. Blue sheets, anyone who did not sign the blue sheets, please do so before you go out, and please bring me the blue sheets. Excellent. Thank you. Yes.